Okay, so the plan for today is to continue with 3.6, talking about logarithms and their derivatives. Take um, a little look at 3.7, rates of change in the natural and social sciences. We won't go into all of the different topics that the book covers. We'll pick a couple of different high points, and that'll be our focus for 3.7. And then jumping ahead to 3.9, related rates. So we're not going to explicitly cover 3.8, but we'll talk about the ideas in 3.8 as part of other chapters or other sections. The quote of the day today is from probably my favorite professor of my college experience, one of my grad school professors, Professor Bill Layton at Pitt. He's retired now. And one of his quotes that stuck with me was, "Good decisions come with experience, and experience comes from making bad decisions." So when you make a bad decision, don't just, feel bad about it, try to learn from it. And I think, a good thing to add on to that is there are several versions of this. This isn't my idea. Certainly, it's not Dr. Layton's quote either, but wisdom is learning from other people's mistakes. So um, my wife and I do rock climbing in a gym, but there are a lot of people that do rock climbing outside, and I like watching some YouTubers. There's one YouTuber in particular who does climbing fails, he calls it. So he takes, three or four clips or so that people have sent into him, and where something went wrong, never like one where somebody dies or something, but they might have kind of gotten injured or took a bad fall or something. Um, and he kind of looks at, all right, well, what went wrong here, right? What could they have done differently? And when you're in that situation, what could you do differently to avoid that same outcome? So learning from other people's mistakes, um, is a good way to learn that saves you the pain of going through the bad experience if you're able to do that. But if something doesn't pan out right, you know, take a look back and ask, what could I have done differently uh, to make that turn out better? Okay, so I think maybe the first thing we'll do today is just kind of a quick review of implicit differentiation, because when we're working with derivatives of logarithms today, we're going to be using implicit differentiation. So we'll warm up with this last problem we skipped over last time, and then we'll jump into 3.6. So here we have uh, a problem where we have an implicit function, sine of pi times x plus y equals 0, and we want to find dy dx. So let's try to solve this problem. I know that the main idea in implicit differentiation is, if I want to find dy dx, I can think of d by dx as like an operation that I can apply to both sides. So just the same way that maybe solving a quadratic equation, I might say want to square root both sides at some point. I can do a similar thing here. I can apply this differentiation with respect to x operation to both sides. The right-hand side, of course, just gives me 0, the derivative of the constant function, 0. And the left-hand side, I have sine of some stuff that depends on x. So to differentiate that, that gives me cos of that same stuff times d by dx of that stuff on the inside. And this is from my chain rule. So now I need to take d by dx of pi times x plus y, but the pi can just come out in front. And then d by dx of x plus y is 1 plus y prime. And that's 0. So I note that if I'm looking to solve for y prime, I note that I can divide through by pi, so that just goes away. So I either have y prime equals -1, or I have cos of pi times x plus y equals 0. And I'm going to focus on, I want to find y prime. So if I pick an x and a y, if I pick an x and a y where I have sine of pi times x plus y equals 0, well, I know that sine of an argument and cosine of an argument are never 0 at the same place, right? So if I pick an xy combination that makes this true, then this cannot be true. I can find x's and y's where cos of pi x plus y does equal 0, but those x's and y's, whatever this curve looks like, whatever it may look like, those x's and y's where cos of pi x plus y equals 0, they're not going to lie on that curve. So I know that this is never what I'm never going to be part of my solution. So I just end up with y prime equals -1, in fact, saying that the derivative is -1 everywhere. Does this make sense? Well, let's actually look at what this curve looks like. Let's come over here. Maybe we'll switch colors. So sine of pi times x plus y equals 0. Well, sine of stuff is 0 when stuff is, well, any integer, a multiple of pi, right? So n pi, n is an integer. We can divide the pi's out, and I see that I have y equals -x plus n, where n is an integer. So actually, sine of pi x plus y equals 0 kind of has a nice simple structure. There's y equals -x plus 0. There's -x plus 1. Y equals -x plus 2. Y equals -x minus 1, and so on. So this this family of infinitely many parallel lines with slope -1 is really what the graph of this relation looks like. Oh, and we can see more clearly now, of course, the derivative should be -1 everywhere, because these are just all lines with slope -1. Okay, any questions on implicit differentiation? So the big idea was when we have a relation between y and x, we can think of applying the differential operator to both sides. All right, jumping down to derivatives of logs then in 3.6. Just a super quick recap of some things from last time. We know that the log function is the inverse function for an associated exponential function. So y equals a to the x is associated with the logarithmic function x equals log base a of y. We know that the domain of the log function is the positive real numbers, where the domain of the associated exponential function is all real numbers. We have some important properties. For instance, the exponentiation operation and the log operation are inverse operations, so they undo one another. We could write that in either of these ways. Very important property that the log brings powers down in front. So the log of x to the n is n times log x, and the log breaks products apart into sums. Log of the product is the sum of the logs. We mentioned that in calculus and in math, we tend to favor the natural logarithm, the log base e. In engineering, often log base 10, sometimes called the common logarithm, is preferred. And in computer science, oftentimes log base 2, lg of x, is used. we had a theorem that we proved where d by dx of a to the x equals a to the x times natural log of a. So in the case that a equals e, the natural exponential base, the derivative of e to the x would be e to the x times natural log of e, but log base e of e, this is like log base e of e to the 1, is just 1. So this is consistent with our previous theorem, derivative of e to the x is e to the x, but this just generalizes that theorem to work for exponential functions with any base, not just the natural exponential base e. And that was where we left off last time. Okay, so let's use that theorem to work out this problem. So I want d by dx of sine of 2 to the x. Now I note that I have a composition of two functions. I have sine of stuff, and then what's being plugged in is 2 to the x. So by my chain rule, I'm going to differentiate the sine into cosine. And I have cosine of 2 to the x times the derivative of that stuff inside. Let me actually write this out in one more step. So this was an application of the chain rule. We haven't used anything about derivatives of logs or exponentials or anything like that yet. And now by our theorem, this theorem up here, we need to differentiate 2 to the x. Well, cosine of 2 to the x just comes down. It's just comes along for the ride. And the derivative of 2 to the x is going to be 2 to the x times the natural log of 2. That's just a number. Natural log of 2 is somewhere in the ballpark of 0.7 or so. That's an important number that comes up in things like half-life of radioactive materials and all kinds of things like that. I see I have a 2 to the x bit, I have a cosine of 2 to the x bit, and I have a number, and nothing really to simplify here. So this is as good as it's going to get. So applying my chain rule, being really careful, as I mentioned last time or the time before, if we're going through any of these notes and you say, wait, where did that chain rule come from? Or if you're still not feeling 100% confident with the chain rule, go back through the notes and something like this, pop off to the side, write out, you want f of g of x. So f of t equals cosine of t, g of x equals 2 to the x. What's f prime of t? What's g prime of x? Piece everything back together with the chain rule. So break it out and, fill in all the details until you get to the point where you can do it without explicitly writing that out. If you're not at a point where you can do it without explicitly writing it out yet, that's fine. That's perfectly okay. We just learned the chain rule, a week or so ago. So that's perfectly okay. You want to get there eventually, in the next week or so, probably. But for the time being, if you're stymied somewhere, just, go off to the side, rewrite that part of your notes a little bit more verbosely and get a little extra practice that way. Okay, any questions on that problem? Okay, we have a theorem. The theorem is the derivative of the natural log of x is 1 over x for x positive. And actually the derivative of log base a of x is also 1 over x for x positive. So we'll prove part 1 and we'll leave part 2 as an exercise. Oh, I have a mistake there. Log base a of, well, we'll do both of them because I apparently made a mistake typing up my notes. I was going to say, wait, that I just read it off of there and said something doesn't sound right there. So we will come back to that one and fix it. All right, so let's start with derivative of log x. So I might be tempted to do something like maybe resort to definition of the derivative. That's going to work. That's not going to work very well, right? Because I'm going to get something like log of x plus h minus log x. But I know that log doesn't work nicely with sums of things as its argument. It kind of works pretty nicely with products of things in its argument, but not so much with sums of things. I don't really see anything related to log x in my, say, section 3.1 theorem that dealt with polynomials and those kind of things. There's not a whole lot that I can do with this. But one thing that I can leverage is, well, I actually know quite a bit how to take derivatives of exponential functions. I have a couple theorems uh, that relate to that. So I don't know how to kind of take a direct attack at this problem. But what I could do is I could set up y equals natural log of x. I want to find y prime, in other words, find dy dx. And if I move that log to the other side as an exponential, right? Remember the association between log base a and a to the power. So I could move that to the other side as e to the power y equals x. And I want to find y prime. Well, now I know how to do this. I apply the differential operator with respect to x to both sides, being careful to use the chain rule where appropriate and being careful with which variable I'm differentiating with respect to and so on. But I can treat this the same way that I treated the inverse trig functions, right? I put y equals inverse trig function, I moved the trig function to the other side, proceeded forward, took the derivatives, used some algebra to simplify things. So I can say that d by dx of e to the y equals d by dx of x. On the right-hand side, this is just 1. On the left-hand side, I have d by dx of a function of y. Well, I can use my chain rule here and make this d by dy e to the y times dy dx. This is really what my chain rule says, kind of in that more differential form. And d by dy of e to the y is just e to the y. And dy dx will just write as y prime, because when I write y prime, it's pretty clear that the derivative that the variable we're differentiating with respect to is x. So I have e to the y prime equals 1, or y prime is 1 over e to the y. And we know that natural log of x is an actual function. It's not just a relation, it's a true function. For each input x, we get at most one output y. So we should be able to reformulate y prime as just a function of x, I would expect, right? I don't need that extra bit of information from the y coordinate to tell me where I'm at on the graph. And indeed, I see that that's the case. E to the y equals x. So I'll just say y prime is 1 over x, which is exactly what we were looking for. And I'll take a different approach to solve this. You can solve this using a similar approach as down here for practice as an exercise, but since I have the wrong thing on the right side here, let's see what it should be. One approach I could take is a change of base, right? I know that log base a of x is log base b of x over log base b of a. Or in other words, log base a of x is the natural log of x over the natural log of a. I know this is true, right? So just taking my change of base formula and using the new base to be the exponential base, the natural exponential base. And then pretty clearly the derivative the derivative of log base a of x is going to be the derivative of log x over log a, or that's going to be this 1 over log a is just a constant. It just comes out in front. That's going to be 1 over x times log a. So I don't know, I don't remember why what caused me to leave this off, but probably just some issue with copying and pasting and so on. I probably copied this down to here so I didn't have to do all the subscripts and all of that and just neglected to change that right-hand side. So would have been quite difficult to prove that theorem because it was wrong. But as an exercise, you can still prove this theorem using this approach, using the inverse function approach. So if you want a practice exercise, you can try that. Now that we have the right thing on the right-hand side. Okay, let's look at this example now. What is the derivative of log of negative x where x is less than 0? To plug into the log function, I can only plug in a positive number, but I can evaluate the log function at negative x so long as x is less than 0, because then negative x is going to be positive. So important that we have that domain restriction correct there. X is less than 0 in this case. So what's the derivative of log of negative x? Well, there's a couple ways I could do this. One of them, we'll just use the chain rule, let's say. So I have log of stuff that differentiates to 1 over stuff times the derivative of stuff. I'm actually going to write this out a little more explicitly so that we see where all the pieces are coming from. But the derivative of negative x is just negative 1. So this is negative 1 over negative x, or just 1 over x. So actually, derivative of log of negative x is 1 over x. I could have taken a different approach here. Well, log of negative x, what if I tried to do something like this? What if I tried to do whoops, log of negative 1, getting my parentheses and brackets mixed up here. Derivative of, let me just rewrite this parentheses. Derivative of log of negative 1 times x. There we go. I think I've got all my grouping symbols sorted out now. And now maybe I want to say that the log of the product is the sum of the logs. And now I differentiate, and this constant differentiates to 0. This derivative log x differentiates to 1 over x. I get 1 over x. So I have, I guess, a second way to prove this, right? What do you guys think? We really want to be careful here, right? I used a log property, a log theorem. I got the same answer. I got the right end result. But I mean, log of negative 1, that doesn't seem like a very good thing to do. Even log x, keeping in mind that x is less than 0, and our logs domain is only positive numbers. So this is valid. I can make this log of negative 1 times x, that's fine. But this doesn't really hold. I can't apply that property because the property of logs, because that gives me 2 logs and I'm trying to evaluate both of them at negative numbers. So I've got to be careful about little details like this when I have um, when I have functions like this that have a domain restriction in them. So even though this really looks like a valid proof, it didn't quite work out. But this would be a valid proof. Okay. So maybe I shouldn't have written it in green. Maybe I should have written it in red. But as a little aside, well, what is the derivative of log of a times x? Just a constant times x. Well, provided that, let's say, a bigger than 0 and x bigger than 0, this is going to be the derivative log a plus log x. Now everything's got the right sign, and now I'm safe with what I'm trying to plug into logs here. This is a constant. It differentiates to 0. This is 1 over x. So this idea was a valuable idea. It didn't work in this specific case, but it maybe helped us out with something else. And maybe, we realized, oh, okay, this doesn't quite work, but maybe that gave us an idea that we could use to solve a different problem, right? Didn't quite work here or in the log of negative x example, but it maybe works to solve a different application. But actually, we see that derivative of log of a times x is 1 over x as well. So it really seems like these log of number times x, their derivatives just kind of look like the log. Okay, so as a corollary, we saw before that derivative of log x when x is positive is 1 over x, and derivative of log negative x when x is negative was also 1 over x. So if when x is positive, I input x into log and get the derivative being 1 over x. And when x is negative, I input negative x into log and get a derivative of 1 over x. Well, that's really just saying if I input the absolute value of x into log and take its derivative, then I get 1 over x. Right? Absolute x is x when x is bigger than 0, negative x when x is, well, I suppose bigger than or equal to 0, and x is less than 0, but we're excluding 0 here. We definitely don't want to log 0 itself. We'd get something that seems a bit like maybe negative infinity, depending on how you look at it. So kind of we can kind of generalize things or pull these couple of theorems together and have the derivative of log of absolute value of x as 1 over x. This will be kind of I don't want to say a majorly important topic in integration and in Calc 2, maybe a minorly important topic, but it's a technical detail that does come up from time to time that if we kind of want to go the other direction, if we want to say like, what's the most general function whose derivative is 1 over x, we probably want to say log of the absolute value of x and not just log x, because log absolute value of x is a little more general. So it's a little side note on that. Okay, let's look at the next example here. The derivative of x times log x minus x. And as an aside, I think I've said this before, but the natural log, I'll basically just always refer to it as the log. If you're in an engineering class, when they say log, log 5 or something like that, like they probably mean log base 10. So context is a bit important here. But again, we kind of also know that logs are only different from one another by a constant multiple. So, okay. So derivative of x log x minus x. Well, I see that my first term, I use a product rule. Derivative of the first times the second is a log x, plus the first times the derivative of the second, derivative of log x is 1 over x, and then minus the derivative of x is 1. Or x over x minus 1, those cancel, and I just get log x. So the function whose derivative is log x is x log x minus x, and log x's derivative is 1 over x. Okay, another example. The derivative of log of 1 plus x squared. Again, I have log of stuff. I differentiate it by the chain rule to be 1 over stuff times the derivative of that stuff in the argument. And the derivative of 1 plus x squared is just 2x. We might start to notice a pattern here when we're starting to differentiate a bunch of these log of stuff type functions. What is the derivative of the log of a function of x? And, we'll presume that things work nicely enough that we can take all these derivatives and so on. Well, I get derivative of log of stuff is 1 over stuff times the derivative of stuff. So as long as well, if g is being plugged into log, the output of g has to be positive for that to even make sense, that original function. So g being positive means we don't have an issue with the denominator g of x, but we probably should assume that g is a differentiable function. So the derivative of log of g of x is g prime over g. Or again, in the future, it might be useful to say if I recognize that I have a ratio that's the derivative of a function over a function, or if I have a denominator with a derivative with its derivative in the numerator, if I want to kind of go backwards, if I want to say this function is the derivative of what function, a question we'll ask quite a bit in integration and in Calc 2, recognizing this pattern is very helpful. That the derivative of log of a function looks like function prime over function. Recognizing that pattern, super helpful for the very end of this course and in a bunch of Calc 2. And you might have intuited that pattern, from some of the examples we did up here. But we can, say, I think I recognize a pattern here. Let's see if it holds in general. And it does, again, as long as I guess g is differentiable. Okay, let's look at this, what appears to be a big mess. The derivative of log of x plus root x squared minus 1. We'd really love to simplify this a little bit. I mean, if this was derivative of log of x times square root of x squared minus 1, I probably would try to use some of my log properties to break this apart and make it an easier derivative to do. But my overall operation inside the log is a sum, and logs of sums don't work super nicely with the log properties, so we're just going to have to proceed, I suppose, by brute force. So log of stuff differentiates to 1 over stuff. And then the chain rule pops out, derivative of stuff on the top. So the derivative of x is 1. And the derivative of square root of x squared minus 1. That's 1 over 2 root stuff. Let me give myself a little more room here. So derivative of square root of stuff is 1 over 2 root stuff. I'll write the 2 there. times the derivative of the stuff inside, but that's a 2x. These twos divide out. Okay, so what can I do now? I suppose in the numerator I can simplify things by getting a common denominator. So I still have my overall denominator and the denominator in my numerator. Square root of x squared minus 1. And I'm going to have square root of x squared minus 1 plus x. So this is, it's starting to run together, but that's a separate line. But I actually noticed that this bit and this bit are exactly the same thing. They actually just all cancel out or divide out. And I just end up with 1 over square root of x squared minus 1. I don't know what my issue was with my square roots and powers. I can't seem to not make them run into each other. There we go. So it actually turns out pretty nicely. It looks a little bit like the derivative of the trig, the inverse trig functions, right? It looks a little bit like derivative of arcsine or arccos, but like the x squared minus 1 is the opposite of 1 minus x squared. And this actually has a tie to the hyperbolic, sometimes just called the hyperbolic functions, or sometimes called the hyperbolic trig functions, which we'll see coming up in a couple sections here. So these hyperbolic functions, quite useful for some applications. And we see that, the derivative of this big mess ended up being something that that probably was simpler than we would expect. I mean, granted, it's not the simplest thing that I've ever seen, but probably a lot simpler than we would have expected initially. Okay, any questions so far? All right, so what about something like this, the derivative of x to the x? Now, I might be tempted to think back to my previous rules. I had, for instance, derivative of x to the n is n x to the n minus 1. I might be tempted to apply that here and try to make this like x times x to the x minus 1, but I know this doesn't really apply because here n had to be constant, right? X to the n, x to the constant, but we want to differentiate x to the x, that's a variable power. Or similarly, derivative of a to the x was a to the x log a, so I might be tempted to make this something like x to the x times log x. But again, this presumed that this base was constant. We kind of have like a mishmash of these two ideas here. So can I leverage either of these ideas to solve this? I don't think directly. I think if I try to use either of these directly, I'm going to be stymied by the fact that I need a constant in the exponent or a constant in the base. And I don't really think this is going to generalize nicely to a situation like this. I think this is a little too different from either of these, these previous theorems we had, to really make good use of them. Okay, let's get rid of these. Okay, so what other options do I have? Well, one thing that I know that we haven't really made use of yet in this section, so it might be a little bit obscure still. But one thing I know is that logs bring powers down. Really, the big problem here, if I can get back there we go. The big problem here is that I have a variable in the base and also a variable in the power. That combination of two things just doesn't work nicely. If I can get that x out of the power, well, then maybe maybe I can make some headway. I can get the x out of the power by logging things, but I can't just say like equals derivative of log x to the x or something like that. I can't just just log it out of nowhere. But I want something like that. So what would I do? Well, I kind of need something to attach the log to in a sense keep track of the fact that we have logged the thing and we can maybe undo it later on. I might be able to try to manipulate this inside, instead of making it x to the x, maybe I can make it like e to the power natural log of x times x. I could do something like that, I suppose, but that's a lot of shuffling around inside the derivative. I think it's a little cleaner, a little nicer from what I call kind of the bookkeeping standpoint to do something like this. Let's set y equals x to the x, and we want to find y prime. Well, before, what I would do is I could apply an operation to both sides. I could apply an operation to both sides, say exponentiate both sides, right? So that I end up uh, with something on the left side that is not trivial, but that I can differentiate. Or I did this with my inverse trig functions as well. If I apply the natural logarithm to both sides, well, now this x can come down in front, and I end up with this. I could have ended up with the same thing, again, if I just worked with just the x to the x and used some log properties. But that's just a lot of shuffling things around, a lot of places that I can make just a little silly mistake. I think going this route is a lot nicer because uh, I kind of have my log attached to the y here over here. It's much simpler to work with rather than I think I would have had to make this what like derivative of e to the power natural log of x to the x, which would then be e to the power x times natural log of x. That's just a lot of symbols, a lot of things happening in the exponent. Really easy to make a mistake in those kind of cases. But this, I think, is more straightforward. Now I apply d by dx to both sides. And on the left side, well, I could use my chain rule here, but let's be a little more verbose just to make sure that we don't make a mistake. So applying my chain rule gives me that. I could have done like 1 over y times y prime and used this idea here. But again, I just kind of took one more step so that we're a little less likely to make a mistake. There's a lot going on here. When the complexity is high, try to take simpler steps if you can. And now I have the derivative of a product, which is much easier for me to differentiate than the derivative of this original kind of variable to a variable thing. So I take derivative first times the second, plus the first times the derivative of the second, or I end up with, well, d by dy of log y is just 1 over y times y prime equals log x plus 1. Or I end up with y prime equals y times log x plus 1. And I know that y is x to the x. And I'll write this maybe as 1 plus log x. And that's what I have. So I have something that actually kind of felt a little bit like x to the x times log x, like if we had applied the derivative of a to the x equals a to the x log a formula. But we would have been off by a little bit, right? We would have missed this plus 1 here. So I don't want to be too flippant about applying theorems where they don't exactly apply. So here we really did have to go this, we really did have to take a different route. We would have gotten a lot closer using the theorem derivative a to the x is a to the x log a, than say using the theorem derivative x to the n is n x to the n minus 1. But we wouldn't have gotten the right answer in either case. So I think I think that's where most people would have started if they looked at this problem, is looking at those two theorems. And I think that's a good place to start. But again, we don't want to be flippant about these theorems. If the theorem says something like something about, say, the derivative of a to the x, where a is a constant, we need to really respect the fact that a has to be a constant, and the derivative of x to the x, variable to a variable, doesn't fit that pattern close enough. Okay, and then last problem in this section, let's try to find y prime if x to the y equals y to the x. We're finding y prime, so we kind of know that we want to take d by dx of both sides. But if I do that now, d by dx of x to the y, that's going to be pretty messy to try to do. Again, I have variable to a variable power. So I think maybe the first thing I'll do is I'll log both sides. And here we're kind of implicitly assuming that the x's and the y's have domain restrictions, so that this is a sensible thing to do. Right, so if we set, say, x and y positive, this would certainly be a reasonable thing to do. That's probably a pretty reasonable domain restriction to apply to the implicit relation in the first place, because if one of these could be negative, then am I going to be looking at like a negative number to the 1/2 power? That's going to be very messy, right? Okay, so on the left side, I get y log x, and that's equal to x log y. So I still have symmetry, but here I'm going to break the symmetry a little bit because I'm taking d by dx. I'm choosing one variable to differentiate with respect to, so I have nice symmetry here, but I might lose the symmetry in this next step. And I have a product rule on both sides. There's a lot going on here. Let me just write out one more step. So derivative of the first times the second plus the first, derivative of the second. That's the left-hand side. And the right-hand side, derivative of the first times the second plus the first derivative of the second. Right. There's a lot going on here. Maybe you could have gotten away with doing all of this in your head if you're really comfortable with all of the different product rule and chain rule and all of that. But I think when there are this many steps involved, just write out one extra line. It reduces the chance of making an error by quite a bit. Going back to that idea from a couple classes ago, we want to decrease complexity before increasing it again. We're gonna be taking all kind of x derivatives of stuff with y. That's already a kind of complicated process. Let's just break everything apart and make the derivatives as simple as we can, so that when we get to something like this, we can just attack that by itself. D by dx of y, well, that's just y prime, and then times log x, plus y, d by dx of log x is just over x. D by dx of x is just 1, so that's just log y, 1 times log y, and then plus x times, now here we have to be careful with d by dx of log y. We could think of this as d by dy log y times dy dx. So this is very clearly a 1 over y, because my variable of differentiation matches the variable inside. This is just 1 over y times dy dx times y prime. And so I get something like y prime times log x minus x over y, bumping this guy to the other side, equals log y minus y over x. We have some symmetry breaking here because we chose to take the derivative with respect to x. So that's why we have like minus signs and things aren't quite symmetric anymore. Because we picked a variable to be the independent variable and let the other one be the dependent. So this is what we have, or maybe we want to write it. Yeah, I think I'll probably just leave it that way. We probably could multiply top and bottom by x times y and maybe make it a little bit nicer, but maybe also make it not so nice. But I think I'll just keep those fractions, the y over x and the x over y. So any questions on derivatives of logarithms, or often this is called logarithmic differentiation, where we kind of log the function first. We set y equal the function or something like that. If we need to, we log first, we differentiate, and then if we need to, we solve at the end. So any questions on this topic? Okay. So moving on to section 3.7, looking at rates of change in the sciences. And like I said, I'm picking a couple examples out of this section. The homework only picks, a couple of topics out of there. So this is just kind of an interesting little, almost like a tangent, just showing you, okay, some of the stuff that we've learned in the last several sections, it seems pretty dry, right? We haven't talked too much about applications. I tried to throw a couple ideas in here and there about, especially with differential equations and things, but I know that most of you are interested in applied fields. Let's try to tie some of this to applied fields now. So let's take a look at relativistic forces. And I think most folks are familiar with Newton's second law. If m is constant, if we have constant mass, Newton's second law says F equals ma, force equals mass times acceleration. But there are situations where we consider mass to not be constant. I mean, one example would be just if, say, you had a rocket and it has some fuel in it, the fuel is part of the mass that the rocket has to pick up. But the longer the rocket flies, the less the more fuel is burned, the more it's, exhausted, the less the rocket's mass is because it's gotten rid of some fuel. So over time, the rocket gets lighter the longer that it flies. Another example is in special relativity, we have kind of rest mass, which is m naught, m sub 0. That's kind of like if a thing is like sitting right next to you and you're measuring it, you're measuring its mass, what would you think its mass is? Versus something like apparent mass, where if the thing is moving past you really close to the speed of light and you try to measure its mass, what would you think its mass is then? And it turns out that, counterintuitively and very strangely, you don't get the same answer. So things like time, things like length, things like mass change whenever the observed thing is moving very quickly relative to the observer. So, I mean, I'll leave it to, one of our physics profs to explain the details or why this should be true or any of that. But it turns out that the kind of appropriate, in some sense, I suppose is the right word, the appropriate correction constant, or the model of special relativity, is that Can I select it here? There we go. That what we want to do is we want to take the rest mass, the mass that we would measure if the thing was just sitting right beside us and wasn't moving relative to us. And we want to divide it by this thing, the square root of 1 minus v squared over c squared. Here, c squared is the speed of light. It's just a constant. But v is the speed that it's moving relative to us. So if I was to put a radar gun on the thing and it's flying by me and I said, oh, it's moving at 99% of the speed of light, then v over c equals 0.99. 0.99 squared is something like what, 0.98. I would do 1 minus 0.98, 0.02, square root that, divide by that, and that would make my mass seem a lot larger. I think that's how it would go, right? If I kept track of all of my units correctly. I always forget which ones get smaller and which ones get bigger, and I think time dilates and length contracts, and so it all has to do with this little thing gamma here, the Lorentz factor. So sometimes you're multiplying by the Lorentz factor, sometimes you're dividing by it, and I always have to think about, like, go through the math and figure out, wait, which way does which one of these go? Our goal, though, is to show that force under this condition looks like this. Or we kind of have F equals ma, that force equals rest mass times acceleration, but it's not just multiplied by gamma. We actually get a gamma cubed out of here, right? So if we're looking at, two cars crashing or something, I mean, they're moving at such small such small proportions of the speed of light, right? That v over c is essentially 0, and v squared over c squared is really essentially 0. So we don't really care about this correction in anything that we do in our day-to-day lives. But if we're investigating like two planets colliding or two black holes colliding or something like that, right? This becomes very important all of a sudden. Okay, so let's try to show this. So we need a little bit of background first. Here, force is the derivative, the time derivative of p of t, where p of t is momentum. And momentum is mass times velocity. So we need to take d by dt of mass times velocity. But mass is given by this thing now. So we need to take d by dt of, what is that, m naught times v over the square root of 1 minus v squared over c squared. Now, I haven't explicitly written out the t's, but velocity is a function of time. So v is really v of t. Okay, so I have a time derivative d by dt. I have a quotient here. I have a v stuck way inside of that square root. I don't really feel like using the quotient rule. So what I'm going to do is I'm going to take this over square root of stuff and bring it up top as stuff to the minus 1/2. So I'll do that. I notice that m naught comes out front. So I'm just going to get m naught times a whole bunch of stuff. And now I have function of t times function of t. I need to make sure to use my product rule here. Super easy to forget when there's so much going on. If you want to explicitly write the of t's, that's fine. I find that it kind of clutters things up a little bit more. If you even wanted to write your v's in a different color, just to remind yourself that they're functions of time, that would work too. But I'll differentiate the first. Well, what's that? D by dt of v times the second plus the first v times the derivative of the second. Okay, I think I've got all my grouping symbols squared away there. Okay, so d by dt of v, what is v prime of t? Well, that's acceleration. What's the derivative of velocity? Acceleration. So I have m naught, this is a, times my Lorentz factor, the thing that's causing all of the trouble now, plus v times, all right, what do I get out of here? Well, here I have a bunch of stuff to the minus 1/2 power. So stuff to a power differentiates to, we bring the power down, we have stuff, and then we take one off the power. Make sure that we go the right direction. We have a negative 1/2 power. Negative 1/2 minus 1 is negative 3/2. Well, that looks pretty good. I wanted that stuff to the negative 3/2, and I kind of see where that's coming from now. But then don't forget, I brought the power down, subtracted 1 off the power, but then I have to differentiate the stuff inside. D by dt of 1 minus v squared over c squared. There's that, and closing one more bracket. Just writing all of this down again. And I suppose at this point I can do minus v over 2. That takes care of those two factors. And now I need to do d by dt of 1 minus v squared over c squared. Well, the 1 differentiates to 0. I can think of this as being like negative 1 over c squared times v of t squared, right? That factor of negative 1 over c squared comes out in front. Then I need to differentiate with respect to t, v of t squared. And that is 2v times v prime. And I'm almost there, right? 2v to the first, and then the chain rule, d by dt of v gives me a v prime. I'm almost there. So I have m naught times, well, I have a 1 minus v squared over c squared to the minus 1/2. And then minus, well, what do I have? I have a v over 2, and then I have a 2v. That's a v squared. So taking care of those three factors, I suppose. The over 2 cancels with, or divides out with the 2, and the v times v gives me a v squared. I have a factor of negative 1 over c squared. That's kind of nice. I know that v squared over c squared is an important quantity here. So that takes care of this bit. What's v prime? What's d by dt v of t? Well, that's just a, acceleration. Okay, so I've got that. I see a factor of a in both terms. So I've got m naught a. That's good. That was something I was looking for. And now what do I have? Well, so I have a plus v squared over c squared times this thing to the negative 3 halves. Well, if I factor out a stuff to the negative 3 halves, if I have, what do I have? Something like x plus v squared over c squared x cubed is basically what I have here. If I factor out an x cubed, what do I need? I need, to make it a little more explicit, x is x cubed over x squared. And now if I factor out an x cubed, I need a 1 over x squared. So I need a 1 minus v squared over c squared to the plus 2 halves plus 1/2 squared coming from here. Right, this way when I multiply all of these together, this is to the plus 2 halves. I would get plus 2 halves minus 3 halves would give me negative 1/2 on that power after all is said and done. So I guess I didn't quite need that much space, but. And now I see in the brackets here, I have 1 minus v squared over c squared plus v squared over c squared. This is m naught a times 1 minus v squared over c squared to the negative 3 halves. And that's exactly what we wanted to show. So we had an application of the product rule, several applications of the chain rule. We saw the chaining part of the chain rule at work here, where, you know, the first application of the chain rule bumps out a derivative, but we need to apply the chain rule there. It bumps out another derivative. We need to apply the chain rule again. So we're adding links to the chain. That's why it's called the chain rule. So I think this is a good practice problem. There's a lot of little details. There's also just a lot of algebra, right? A lot of things that we had to get right with what are variables and what are constants, making sure that we factor things out correctly, making sure we do things like keeping track of the negatives, those kind of things. So just kind of a general all-around good practice problem. Okay, and the other example we're going to look at in this section is a few growth models. So models for things like population growth. The kind of fundamental, foundational, most basic growth model is called the Malthusian model, named after Thomas Malthus. I think he was maybe like a monk or a friar or something, if I remember right. I don't know. Might be confusing, the story, but back a few hundred years ago or something, he came up with this idea for this model. And here, population at time t is p of t. And the model is simply dp dt equals kp. In other words, the rate of change of population is proportional to the population. This kind of makes sense, right? If we have twice as many people in the population, they're probably going to be like twice as many births each year, right? I think that's kind of a pretty reasonable expectation. Or if everybody in my population dies out and p is 0, then my population doesn't spontaneously just start to reemerge or something like that. So in population 0, if p is 0, the rate of change is 0, and we never go away from 0. So we know, for instance, that p of t equals 0 is a solution just by kind of looking at the differential equation. Let's try to work on finding a general solution to this differential equation. This is almost the simplest differential equation we could write down that's not completely trivial. But we're looking for a function for which its derivative is proportional to itself. Well, if we thought of something like P of t equals e to the power t, well, then P prime of t is e to the t is just P. So I don't quite get that extra factor of k out of there that I need. If I thought of something like, well, I mean, of course, if I try to say add k or something like that, the derivative just gets rid of it. So then P prime doesn't really look like P at all. If I try to multiply by, say, a factor, k, like this, maybe P of t is k times e to the t. That would be a pretty reasonable guess. But I actually noticed that P prime is, again, exactly k e to the t. It's just exactly P. I didn't get my factor of k that I need to get out of there. So where can that factor of k come from? I get rid of that one too. What if I put it in the exponent? So e to the power kt. Now when I differentiate, I have e to the stuff differentiates to e to the stuff times the derivative of kt, which is k. But now I have k times the original p of t, right? K e to the kt. That's the solution. That's e. So this is a solution. Is it the most general solution? Well, I kind of noted just by thinking about just looking at the differential equation itself, I noted that P of t equals 0 should be a solution, either because it's kind of sensible that if P equals 0, then the right-hand side is 0, P prime is 0, I have no rate of change, so I just stay at 0, or by just simply looking at, well, the function P of t equals 0, its derivative is 0, and I have 0 equals 0. So I could think of it more kind of from the standpoint of the population growth model side of things, or just from the flat out calculus and algebra and so on. But I see that P of t equals 0 should be a solution. And in fact, I would guess that I should have different outcomes on my model for different starting populations. If I start with 100 people or a million people, and I have some growth rate k, I shouldn't have the same number of people over time. And so it turns out that we can account for that by putting in some arbitrary constant a. Let me actually move these over just a tad. There we go. When I differentiate a e to the kt, that a just comes along for the ride. And I notice that the a e to the kt makes up p now. And I still get that factor of k. So if I look at this model, this still is a solution. It actually does include this P of t equals 0 as a solution. That would just be the special case a equals 0. But this actually represents a family of curves. So it's a family of curves like this. In fact, we notice that P of 0 equals a e to the 0, or that's just a. We could even give a more descriptive name, like something like P naught. This is the population at time 0 is really what a is representing. So it's just this y-intercept there. And then, of course, I have this kind of degenerate case where my population is at 0 and just stays at 0 forever. I suppose in theory, A could be negative as far as just say the math goes. A could be negative. That would be, perfectly valid as far as the math. But for population in this application, it doesn't make sense for us to say we have, negative 100 people or something. But maybe in a different application, it might make sense to have negative outputs from your dependent variable. So we could have exponential growth kind of away from zero on the negative side as well, mathematically speaking, but we'll really not consider those cases because we're sticking to growth models, population growth models. Okay, so that's the Malthusian model. Its benefit is it's pretty simple. This is simple exponential growth. It's simple to explain where all of the pieces come from. It's just about the simplest differential equation you could want to solve. It's probably the simplest non-trivial one. And probably in the short term, it probably does pretty good for most populations. If you can estimate the population growth rate, if that stays reasonably constant over, 5 years, 10 years, you can probably do some good work with this. Probably the clearest problem with the Malthusian model is, well, our populations grow without bound, right? Clearly, we know that's not the case. That might be, that might be a characteristic that we don't practically care about. If we're only using this model, say, to predict human population over the next 10 years, are we really going to, theorize that we're going to end up with so many people that like nobody like will all just be standing, on the surface of the earth like we were standing in an elevator, nobody can even move, like, of course not. But the further we go out, the further we go out in time, exponential growth grows really quickly, the bigger a problem that is. If I want to estimate how many people there are going to be 1,000 years from now or 2,000 years from now, I probably don't want to just keep exponentially growing like this over that much time. We're likely to run into some practical difficulties there. Okay, so I would like something that has this flavor to it, but that maybe doesn't shoot off to infinity. So here's where we enter the logistic model. And again, in differential equations, in the differential equations course, we talk a lot more about the details of these models and some different characteristics of them. We work through solving them very carefully, not just taking the approach up here where like we just kind of guessed a little bit and said, well, this seems to work out, well enough. We go through and we carefully, you know, uh, derive all of these solutions and all of that. So this is not intended to be an enormously rigorous treatment of this material. Okay, so looking at the logistic model, notice that we have as its base the Malthusian model, P prime equals Kp. But then we have another factor here, times n minus p. Let's look at the behavior of this solution. Again, I have some, say, over time. Here's population. If I have just a little bit of positive population, then kind of in the short run, I'm going to have nice exponential growth from this Malthusian bit here that this is built off of. If I have a little higher level of population, still probably some exponential growth. But I'm going to get to a point, particularly the point n, where, well, n minus p actually becomes 0. What happens when n minus p equals 0 or when p equals n? Well, in that case, p prime equals 0. So at n, p prime equals 0. In other words, p of t equals n is a solution. It's an equilibrium solution to this differential equation. If I ever have a population that starts out with n units of that population, it's just going to stay there forever because p prime will be 0. It'll never deviate from n units. There's never going to be an increase or a decrease in that population. So at n units, I have this nice equilibrium solution. What if I have a population that's bigger than n? Well, here, and I should have said k is bigger than 0. Here, k is bigger than 0. P is, of course, bigger than 0. But if p is bigger than n, then n minus p is less than 0. P prime, the product of these three, is going to be negative. If I ever get a population that's above n, and actually that population decreases over time. And in fact, as I get a population that approaches n from below, my rate of change of the population, my n minus p factor, is getting closer and closer to 0. I still have a positive rate of change, but it's much smaller. So I actually end up with these kind of logistic functions, as they're called, for solutions. They have kind of an exponential growth phase, but then essentially, roughly speaking, when resources start to get scarce, populations don't grow as fast. When there's in say wild animals or something, when there's food scarcity, their populations don't grow as fast. When there's a very small population relative to the amount of food available, their population can grow exponentially. But once they start to hit that upper bound of where they run out of food or run out of um, yeah, territory or something like that, then the population doesn't grow as rapidly. There's another interpretation of this that's something along the lines of like this factor p squared here is, if you have like p number of people in a room, the number of possible interactions between two different people scales kind of like p squared. So there's also an argument about like people. Well, the more people we have in a certain, you know, geographic area or whatever, maybe the more fighting there is, and so on. So maybe that's a pullback on the tendency for population to increase. So we actually see something like exponential growth to a limit, and if we surpass that limit, exponential decay down to that limit. This is maybe a better model. It avoids that P of t going to infinity problem. That doesn't happen anymore. As kind of an aside, on the negative side, if P is less than 0 and K is positive, if P is less than 0, clearly N minus P is positive. We actually do get exponential exponential growth away from 0 on the negative side. So there's no kind of fix, so to speak, on the negative side down here. That's a side note. It doesn't really apply to the population scenario, but we could use this model for other things that might apply to. But yeah, so we have the logistic model, and let me copy the solution from over here because I will never remember it, and it takes quite a while to figure out what it is. Okay, so this is just n times that. So here, n is our carrying capacity. It's our maximum population that can be supported in whatever way that means. K is the natural growth rate of the system, this kind of Malthusian growth rate. And A is an arbitrary constant. It's the thing that by tuning A, you say whether you're on this or that or that or that solution curve. these solutions to these differential equations are families of curves. So by picking different values of A, we can we can pick out a different solution curve. We can overlay our model onto reality maybe a little bit better by matching some parameters. So if I had a certain population I was interested in modeling, rabbits in this certain area or something, and I know that I started with, 100,000 of them or something, then I would choose A. I don't think A would be exactly 100,000 here, but you would figure out, you set P of 0 equal 100,000 and then figure out what A should be in that case. Okay, so any questions so far in any of this? All right, and then the last thing we'll talk about is um, it's a little bit of a different population growth model. This isn't maybe one of the more standard ones. The two most common ones are the Malthusian and the logistic model. But I think it's kind of an interesting one. So let's consider growth on boundary. So the idea kind of here is, uh, let's say we have some bacteria that we have in a petri dish. So this is kind of a two-dimensional surface that they live on. And these bacteria, they all kind of are, clumped together like this. Now, different bacteria behave very differently. So some bacteria will they're happy to crawl on top of one another and grow upwards, and some of them will push out to the side. But we'll say these bacteria, the way that they behave when they try to grow is they grow on the boundary. The guys on the inside don't have any extra space. They don't want to divide and get bigger because they're getting sensory input from around them that there is no space this way or that way or that way. So they also don't want to grow up, because if they divide and go up, then maybe they don't have as direct access to the growth media that is in the petri dish that they're on. So the growth only occurs on the ones at the boundary that have room to grow laterally, right? This could also be something like, humans in cities. And well, I suppose in some sense we can grow up, but that's quite expensive to do, to build skyscrapers and things. So we quite often are restricted to growing out. Um, don't draw too many inferences or whatever from me saying the humans and bacteria grow in maybe the same boundary kind of way, but there's no deeper meaning to it than the two different examples. So if I'm interested in modeling the population, or I'm kind of annoyed at myself for using A up here. Let me switch my variables. I'll use P. P will be the population of bacteria. I use an arbitrary constant A up here, and I don't want to get confused between the two problems. So we'll just keep the variables the same. So dp dt equals k root p would be the model for this, where p is something like the number of bacteria, or something like their mass, or something like that. But I know that P is going to be proportional to area. It's really area is the reason I chose the ADT equals K root A. But P is going to be proportional to area. The number of bacteria on this plate is going to be proportional to the area that they take up. And area is pi r squared. So the number of bacteria is going to look more or less like pi r squared for the radius of this circle. But the growth is on the circumference, which is 2 pi r. But if p is pi r squared, then r is what? P over pi, the square root of that. So the growth is along the circumference, 2 pi r, or 2 pi square root of p over pi. This is what dp dt should look like. And so we see dp dt equals, well, 2 pi over root pi, that's whatever constant that is. times the square root of p. So this growth on the boundary idea, if we have kind of a roughly circular shape, we get dp dt is k root p. Even if we really didn't have a circular shape, this idea generalizes pretty reasonably in a two-dimensional, blob. The area is going to scale more or less like the square um, of the boundary line, of the size of the boundary line. So, I mean, I suppose if you had a really wonky blob, maybe that's not quite true, but if you had a square or a pentagon or something like that, it's going to roughly be true. Okay, so what are we looking for as a solution P of t? We're looking for a p such that more or less p prime equals square root of p. I mean, we have some constants and things, but this is the general structure. Can I think of a function whose derivative is the same as the square root of itself? This is kind of a hard question. It's kind of a non-intuitive question, but if you just go through your catalog of simple functions, you should pretty quickly come upon p of t equals t squared, a quadratic function. If I differentiate it, I knock one off the power, the second power goes to the first power. And if I square root it, my second power square roots to first power. So I use this kind of in quotes. And it turns out, I'll leave it as an exercise to check that this is correct. It turns out the P of t equals kt plus c over 2 all squared satisfies dp dt equals k root p. Right. So I mean, P of t equals t squared doesn't exactly work because the derivative looks like 2t, not like t. So there's a little bit of correction with constants and stuff. And then we also need to incorporate k in here somehow. So, right, I mean, that's why these are in quotes. But we can just with very basic calculus see the broad strokes here, right? And maybe make guesses at the broad strokes of what the solution would look like. And indeed, that would have been a correct guess that we have a quadratic coming out. It's a complicated looking quadratic function in t. That's all that it is. Something t squared plus something t plus constant. Okay. Any questions on any of this? Okay, so our next topic is related rates. It's a pretty big topic. I think with only 7 minutes left, I was thinking of getting through maybe one motivating example today, but with only 7 minutes, 6 minutes now, we're not going to have time for this example. I would recommend, taking a look ahead through the related rate section, just taking a glance at it. It really leans heavily on these ideas that we've discussed so far, things like the chain rule and implicit differentiation. So in preparation for next week for related rates to make pretty good sense, make sure again that you're, pretty confident with the chain rule. You should be getting pretty confident with that now, and that you're confident with implicit differentiation. So if you're confident with those two things, related rates will make a lot of sense. If you're really struggling with either or both of those, related rates is going to be really hard to understand. So for 3.9 for next week, hit chain rule and implicit differentiation. Make sure you're squared away on those before we get to next week's class. So I'll stop the recording.